Last time we started section 4.4 called the Fundamental Theorem of Calculus, and we'd encountered actually two fundamental theorems of calculus. The first version looked like this. It talked about the fact that we can take an antiderivative, we can evaluate it at the upper limit, we can evaluate it at the lower limit, we take the difference between the two. We talked about the fact that that actually finds a net area in terms of a graph. We are not going too far down the trail of what that means further. That will happen in Calc 2. But we looked at this version and we actually did some examples. Where we left off last time was on this version. And I told you that the gist of it is that it's saying that if you take the derivative of the antiderivative, you get back the same values that you started with, right? There is a caveat to that. It's not quite that simple. But in some cases, it is that simple. So the first one we're going to look at, I'm pretty sure, is an example where it is exactly that simple. So if you take a look at, I take it back. It's got the caveat to it already. It's the second piece that has the other one in it. I'm sorry. All right, so if you take a look at this, it doesn't quite look like what's going on over here. And in particular, let me show you the piece that looks different. It's right up here at the top. This says that the upper limit of integration is the variable x. Are you with me? Over here, however, it says that the upper level of your integration, your upper bound, is actually not just x, it's actually a function of x. Does that make sense? It's sine of x. So what I'd like to do is I'm going to do this problem out sort of longhand so you can see what it would actually be. And then I'm going to show you the shorthand caveat to this particular one right here. Okay? So if we were to do this longhand, what we would do is we would first take the antiderivative. So t plus 2. So what is the antiderivative of t plus 2?
T squared over 2 plus 2t.
Perfect. Everybody good with that? All right. And then what we learned in the last piece of material of this section, last class period, is we write our upper limits of integration and our lower limit of integration right here. Right? Okay. And then we evaluate with them. Now, we evaluated with the numbers last time, so we plugged in, like 5 and 2 or something like that. And one of these is a number, the 0 at the bottom, but the other one's actually a variable, but it works the same way. It just means that your calculator doesn't spit a number out at you and draw pretty pictures, right? So this means that I've got sine squared of x over 2 plus 2 sine of x. And then I have that subtracted, and it's not a very exciting one, but I'll write it in nonetheless. 0 squared over 2 plus 2 times 0. Not exciting because it's just nothing at the end, right? Okay, so is everybody good so far? So what I actually end up with here is this is f of x. And if I clean it up just a little bit, I'm going to put the 1/2 in front just because it's easier to see it that way. You don't have to, but... Okay, everybody good with that so far? I haven't actually done the directions. I've just done half of the process. The directions actually say to find the derivative, f prime. So I took the antiderivative because the symbol on the right-hand side had that notation. Right? It was sort of embedded inside the problem, right? And then I want the derivative of what I just found. So I'm going to go back in the other direction now. All right, so what we notice is that we have a power rule because there's a 2. So the 2 comes down times the 1/2 in front. So this ends up being 1/2 times my 2. I rewrite the inside function. This is a chain rule, sine of x, and it'd be to the power 1 if you want to decrease that power. And then because I've got a chain rule, I have to take the derivative of sine of x, which is cosine of x. Okay, and that's the first piece of the problem, the first term. The second term is just 2 sine x. So what's the derivative of 2 sine x? 2 cosine x. And if I just clean up a tiny bit, I really have sine x, cosine x, plus 2 cosine x, and I'm done. And there's nothing particularly crazy hard about what we just did. And you could do it that way every single time if you wish. It would not hurt anything. You take an antiderivative and then you take a derivative. So how does that play in with this particular theorem? That's what I'll show you next. So I'm going to make this just a little bit smaller and shift it over to the left. What the theorem over here says that I should be able to do is that I should be able to simply replace in this function the t with x. And x, as you see, is that upper level of integration. So if I try to do that sort of as it sort of just flat out says, it would kind of look like I would end up with, instead of t plus 2, right, I would end up with sine of x plus 2. Now I'd like for you to compare that answer in red right now to the answer I'm supposed to be getting. How are they different?
Factored out a cosine.
That's right. There's a cosine missing from each piece, right? Do you see that? Like if I took my answer that's down here in black and I were to factor out that cosine like Jeffrey said, I would end up with that same expression that's over there, sine x plus 2. So why? Why did that happen? Well, that happened because what's the derivative of sine of x? Cosine of x. So if you take a look over here, I didn't have to worry about that in the way that the definition is set up, because what's the derivative of x? 1. So over here, there's this understood the derivative of the upper function, I'll call it that. Now, the way that's set up is that if the upper function's x, it doesn't have a derivative that will affect anything, right? It has 1. I mean, the derivative of x is 1, and that's fine. But it doesn't change the answer. Over here, if I recognize in a problem that I have a derivative that's going to affect the answer at the end, that is, its derivative is not 1, right, sine x, then the only thing I have to do at the end of this problem is I have to multiply by the derivative of sine x, which is cosine of x. So this would be sine x cosine x plus 2 cosine of x. And if you compare, the part that's in red's a lot less writing, right? That's the only caveat. That if my upper function is not just x, after I just do the substitution, right, I have to multiply by the derivative of that upper function. Does that make sense? And the reason is because it embeds a chain rule involved in it. That's what happened actually in the process, right? That's where this cosine of x came from, is because I had a chain rule involved. So let's try another one so you can see it happen again. If you notice on this one, though, there's another piece going on that's a little bit different. So take a look at this. How is this problem different than, in particular, this expression on the left? On the left. So compare this, the integral from x to 3 minus x of t squared plus 4 to the integral from a to x of f of t dt.
We're subtracting x.
Okay, so I think what you're telling me is that the lower limit of integration isn't a, it's x.
Yeah, there's a lower limit. Yeah.
Yeah, so, and that is different. There is an interesting thing that happens there. The reality is that in this particular problem, the upper limit and the lower limit are both variables. Okay, does everybody see that? Okay. And this over here is hinged on the fact that the lower limit is a constant. And while it sort of didn't matter on this problem, because when I evaluated it at 0, it came 0 anyway, think with me for a moment. What if I evaluated this and I didn't get 0 and I got, say, 7? In the next step, when I take the derivative down here of 7, what would happen? I'd get 0. It would go away, right? But that doesn't happen if my lower limit of integration is not a constant. It will always happen if it's constant. It doesn't always happen if it's not a constant. Okay? So here's what we're going to do. Do you remember we had a theorem that said if the integral from a to b of f of x dx is such that there's a c between them like this, that I could separate my integral and to go from a to c, and then I could go from c to b. And visually, what we were saying is that if I start at A and I go to B, if I sort of stop somewhere in between, it didn't even be halfway, but if I stop somewhere in between and I were to do the integral here and then I were to do the integral here, it'd be the same thing as doing the integral for the whole piece. We talked about that. That's the property we're going to use for this. So let's see how that looks. What we end up doing is we end up taking our first integral and it will go from x to some constant. And the reality is it doesn't even matter what the constant is. So we might as well use 0 because it doesn't matter. And I'm going to write down that same limits of integration t squared, or the same function inside, excuse me, t squared plus 4 dt. And then my second interval is going to go from that 0 up to the 3 minus x of t squared plus 4 dt. So I'm just separating it into two pieces. And the reason I am is because that allows one of those two limits of integration, the upper or the lower, one of them is a constant. The other one's still a variable, but one of them is a constant. Okay, everybody good so far? I haven't actually found anything yet. I've just rewritten it. So this is the same f of x that we began with. Now, the second piece, the integral from 0 to 3 minus x, it looks a lot like this particular problem. Started with 0, I went to some other function, I've got the antiderivative. It looks the same, it mirrors that. But the first piece still has sort of a problem. What's wrong with that first piece when I compare it back to this order, the left-hand side of this particular function? Yeah, the variable and the number are in the wrong locations, right? Okay. But again, we had a theorem. So this is one of our theorems, if you will, that we're applying. The other theorem that we had is that it said that if we go from a to b of f of x dx, it's the same thing as if we go from b to a of f of x dx with a negative in front. So I can switch the order of integration as long as I change the sign. Right? And that's happening because anytime we subtract, think about just the integers for a moment, like 5 minus 5 is the same as, 5 minus 2 is the same as 2 minus 5, except the signs differ, right? Anytime you do a subtraction, it works that way. So I'm switching the order of subtraction, so I change the sign. So on this particular problem at the beginning, all we need to do to get the order to have the number at the bottom is to put a negative out front. Now I can go from 0 to x of t squared plus 4 dt plus the integral from 0 to 3 minus x of t squared plus 4 dt. Okay, the front end work on this is a whole lot harder than the actual application. We had to manipulate things to actually make it look like this. Why did we do that? I mean, why didn't we just treat it the way that I did over here on the left-hand side? Well, we could have. And if you want to, you can. It won't hurt anything. It's just that it's more work. So we had to work a little bit to get it set up in the right order. But now that we've done that work, everything else is super friendly. Because what it allows us to do is it allows us to take the derivative now without actually doing any of the work. Namely, I don't have to do an antiderivative. And then I don't have to follow that up with a derivative. I can simply evaluate. So the negative at the front stays. The t becomes the upper function, which is x in this case. So I have x squared plus 4. And I'm done with the first half of the problem. Just like that. That's what the second fundamental theorem of calculus says I can do if things are set up in the right order. Now I almost get as much freedom on the second piece too. Like it's almost as freeing, I should say. I am still going to do the replacement much like I just did, right? So over here, the t is going to become 3 minus x squared, of course, plus 4. But there's one additional thing I have to do. I have to do what I did over here at the end. What did I do? How did I get that, or why did I get the cosine of x at the end? Right, I need the derivative of the upper function. And in the second function's case right here, this is not just x. So I need the derivative of 3 minus x, but it's not unfriendly. What's the derivative of 3 minus x? It's just -1. So again, that's pretty friendly. And I can actually just clean up a little bit of algebra now. So at the beginning, I have -x squared minus 4. Over here, I need to, of course, factor that out. So it's 3 minus x times 3 minus x. And if you distribute or FOIL, you get 9 minus 6x plus x squared, right? All of that is affected by a -1, though. So I'm going to go ahead and distribute the -1 through at the same time. So I have minus 9 plus 6x minus x squared. And then that negative, also affects my 4. So then minus 4. So there's all my pieces. And I'll combine like terms. So in combining my like terms, I have -2x squared. Let's see, plus 6x. -4, -9, and -4 is how many?
17.
Yeah, -17. Oh, good. That's what my paper says. It's always a good thing when you get what you got the first time. Okay, any questions on that? These changes that we made with these properties of integrals were really important, because if I don't make those changes, I can't use the second fundamental theorem of calculus. I just can't. It doesn't have the same format, the same form, and if it doesn't have the same form, it doesn't apply. It's kind of like when we did the intermediate value theorem and we said, what are the conditions? Do the conditions apply? And if they don't apply, then the answer is simply that I don't know if the result's going to be true, right? Same things here. I have to have the initial conditions set up, which means the initial form has to look the same. All right. Couple more things in this section. We're so close to done. It's scary. All right. On this one, the problem is actually much the same as the earlier ones we did in class last time. It's simply not giving us the equation set up. It's asking us to set it up ourselves. So this one talks about finding the given area. It says it wants the area of the region bounded by y equal x squared and x equal 2 and the x-axis. So you guys know what all of those equations look like, and you're just going to draw them all on the same graph and see what's bounded. So bounded means trapped. Okay, what's trapped? Where is the space trapped? What is the integral I can set up to show that? So we're going to take our graph. I will use a different color to draw each of my curves. So the first one is y equal x squared. Okay, that's not what I meant to do. Let's try again. Oh, I'll use red. Okay, it looks something like this, right? That's y equal x squared. Let's use green. I'll use green to draw x equal to 2. What does x equal 2 look like as an equation? Yes, it looks like this. It is a vertical line at 2. So over here at 2, I have a line. So this is x equal to 2. And then the x-axis, of course, is the horizontal axis that's already drawn in, right? So if I draw that over, I'll draw it in blue down here. So this is the x-axis. And hopefully you see that there's sort of a triangular-ish shaped region. It's not a triangle, of course, because it's bounded by a curve, but it has the same sort of image right in here, right? Here's my brightly yellow shaded, which you can't see on the yellow backdrop. That's silly. How about orange? That's a little bit better. So it's that triangular shaped kind of region. Okay, but it's not a triangle. So I can't just do like 1/2 base times height and get an exact answer. That would not be correct. But I can use an antiderivative. So the antiderivative, I'm going to move from the left hand to the right hand endpoint of my trapped region. What is the left hand x value of what's shaded in orange? The left hand side. 0. Yeah. So I'm at the actual like origin, right? That's where the shading actually begins. If I had drawn it a little bit bigger, it'd be easier to see. And where will I stop in terms of my x values with my shaded trapped region? 2, right? It's that green line x equal to 2. And then the function means what graph am I shading beneath? That's the red curve that I drew, and the red curve was y equal x squared. So my function is simply x squared. And I put dx to indicate that my variable in my function that I'm working with is x. Now the beautiful thing is that that's a pretty simple antiderivative. So what is the antiderivative of x squared? X to the third over 3. And I don't need a plus c because I'm going to be evaluating. I'm going to be evaluating at 2 down to 0 and evaluating at 0 in polynomials is always fun. So I really have 2 cubed over 3 minus 0 cubed over 3, which is, of course, 0. What's 2 cubed? 8. So this becomes 8 over 3 minus 0, or 8/3. Okay? So these problems where they actually ask you to set it up, you should be able to take what they're giving you and either sketch it by hand or maybe in your calculator if the functions are a little bit more complicated, and look at what area is trapped. Almost always they're trapping it with the x-axis, kind of that's the point, right? And then they're giving you some other kind of trappings along the sides for the other pieces. Okay, there's one last piece of information in this section that we're going to look at, and it's called average value. All right, so you guys know what an average is. Canvas does it for you all the time, right? Class averages, stuff like that. So an average for this works the same way. Let me just let you write this down, and then I'll describe it visually. It says if f is integrable on AB, then the average value of f on AB is 1 over b minus a times the integral from a to b of f of x dx. And I'm just going to draw a bigger version of the graph we just had. Okay, so imagine that the part in yellow, orange rather, the part in orange were somehow made out of like clay or Play-Doh. Okay? It's got a specific area. I know we have to pretend like it's infinitely thin so that it doesn't really make sense to do so otherwise. So you're going to stay infinitely thin as you shift and move things around. But what you're wanting to do is you're wanting to shift that space so that it fills in a nice rectangle instead. Okay? So it's going to have the same amount of area. It's just going to be distributed differently. All right? I mean, you've seen that happen before with rectangles and squares, right? They have the same area, but they're different shapes. Agreed? That's what we're doing with average value. We're taking a graph that's sort of a funny shape, right? It's a non-standard shape, and we're changing it, and we're saying, okay, but if I were to manipulate it and change it into a nice, neat little rectangle, what would the height of that rectangle be? What is the average height overall for this interval? And if you can imagine, and I don't know that I'm going to be able to draw it perfectly, but if you can imagine something like this might be reasonable. If I were to take this upper piece of orange, it's on the top, and I were to shift it over, it might fill in right here or fairly close. If I drew it better, it might be better, but it would fill in that space and I'd have a rectangle of the same area, and instead my rectangle would be this red rectangle, right? And it would have the same area as the orange non-standard shape before. And this piece at the beginning should come as no surprise as to why that's happening. What you're doing is you're dividing by the width of the interval, right? That's what b minus a is. b minus a for this problem is 2 minus 0. It's just the width that you're dividing by, right? So area is length times width. So if I take the area, because that's what this is over here, this is the area, and I divide by the width, I should have the length. Okay, that's where it's coming from. It's just your basic area formula for a rectangle. And the manipulation for it is super like what we've already done. The only difference is that at the very beginning, I multiply by 1 over the width. Or you could say, I take the area that I find, and then I divide by the width. So on this particular problem, we have, in this case, a square root function. And I have the interval going from 4 to 9. So my interval, and you can draw a picture if it helps you. I don't know that we really need it at this point after I've already drawn the other one, but it's going to go from 4 to 9. What is the width of the interval if I'm going from 4 to 9? It's 5, right? So I'm going to divide by that width. It's 1/5. Or if it helps you, write it out as 1 over 9 minus 4. I don't care. It's the same thing. And it's the square root of x dx. Now, of course, square roots are not particularly friendly versions of themselves to do antiderivatives for. A friendlier version is its power version, x to the 1/2. So, what is the antiderivative of x to the 1/2? Okay, so it's x to the 3/2. It would be dividing by 3/2, which is the same as multiplying by 2/3. And then I'm supposed to be multiplying that by 1/5 in front. And I need to evaluate that from 9 down to 4. And I hope you recognize they're choosing 9 and 4 on a very, very good reason. Because I'm going to first change that x to the 3/2 just so you can see it. You can do it without doing this. You can grab your calculator and get it. But if you take a look at this at the beginning, well, first this is 2 over 15. X to the 3/2 is the square root of x cubed. You can put the cubed on the outside or the inside, it doesn't matter. And it's 9 to 4. So because I have a square root still, they've actually chosen very friendly values on this particular one to take square roots of. That's why the 9 and the 4 are showing up. It's not always going to work out that way, but that's actually why this particular one did. So if I take 2/15 and I have the square root of 9 cubed, and then I have minus 2/15, and then I have the square root of 4 cubed. You can square root first, or you can cube first. On this one, it's nicer to square root first because the number gets smaller before it gets much larger. So what's the square root of 9? 3, and then I've got 3 cubed, which is 27. So I have 2 over 15 times 27. And of course, you're welcome to grab your calculator to do that. You don't have to do it in your head. This one's just kind of friendly to do. And then over here, the square root of 4 is 2, and then 2 cubed would be 8. So go ahead, if you will, at this point then, since now we're working with the funny fraction of 2/15. What do you get when you take 2/15 times 27 minus 2/15 times 8? 38/15? That's what I have too. Fabulous. 38/15. If you try to do a decimal approximation, it's not going to work very well on that because there's a repeating decimal that shows up. So you would not want a decimal for that particular one. If a decimal terminates, fantastic. If it doesn't, let's leave it as a fraction. Any questions on that one? So the only thing average value does differently is it puts this fraction that's 1 divided by the width of the interval in the very beginning. And then otherwise, it's exactly the same. That's all I have for you today. Have a wonderful week. I will see you guys on Monday. Dr. Marsh will be here on Friday to do a quiz. And then this 4.3 and 4.4 is what the quiz is over, and 4.4 is due on WebAssign on Friday.